Alpine have always made pretty top quality amplifiers, and I want to see if that still holds true today. We're going to look at a few today. We're going to start off with the A70F, which is a little older, but it's still a relatively modern amplifier from Alpine. Let's start off by looking at the power supply FETs. We have AU-IRF SL8407. Now, these are ridiculously chunky FETs, and they are specifically for use in automotive environment, which is much harsher, so they're a bit more stable in the varying environments you get in a car. Ridiculous current handling ratings with 1,000 amps of pulse drain current. We'll get to that in a minute though. Pretty fast as well, with not too much input capacitance. In the power supply it's lower switching frequency, so it doesn't matter too much. But this is the graph that's really important, and you can see here that most of those specs that look really good are limited to sort of the 2 to 5 volt range here. In the vehicle this will be used at sort of 12-14 volts, so somewhere in between here. And you can see that the ratings drop off a little bit down here. We're not getting anywhere near 1,000 amps, obviously. The switching frequency in the power supply will probably put it up here somewhere, so it's still monstrously powerful. And to be honest, completely overkill for this little 4-channel amplifier. They didn't need to use these at all. I love seeing these fuses in line with the low side drain of the power supply FETs, so if any of these shorts, then you won't get this avalanche of current dumped through the MOSFET to ground, basically causing a little fire inside the amplifier. These fuses will blow first. Now you notice I said low side, and that's because the power supply in this amplifier is actually set up in low side and high side operation. Notice how there's no fuses on these ones. That's because these are the high side FETs for the power supply. If you've ever repaired a car amp, you'll be used to all the power supply FETs having 12 volts from the power terminal through the transformer on the back of them on the drain, which we do have on the low side FETs here, as you can see. However, the ones next to them don't have that. They just have nothing on them whatsoever to start with. Only when you apply the remote do you get switching on the back of the high side FET, and it's not quite as high amplitude as it would be in a regular car amplifier either, only up to 8 volts RMS. Small correction, the ones that have 12 volts on the drain of the FET and the fuses in line are the high side FETs, and the low sides are the ones that have the PWM on the drain when the amplifier starts coming to life. I don't know enough about switching power supply design to understand the benefits or drawbacks of having them in this setup versus just having them all, I think, low side, but it's something to bear in mind, and there must be a reason they've done this. These are the drivers for the power supply FETs, LM5109Bs, and you can see that they are in fact high side and low side drivers. When we power on, we have a ramped duty cycle for soft start, and the switching frequency is 37.1 kilohertz, a little bit higher than usual, which is nice to see. And the PWM on the low side gate settles off at just over 46% duty cycle. We have a massive reverse polarity protection diode here by the power terminals, so if you reverse the polarity, current will be dumped through this diode instead, hopefully, of going through the FETs and killing a bunch of components on the board here. I'm a fan of this transformer style used in car audio application because they are far less susceptible to vibration damage, which is great to see. 2 transformers stepping the primaries up on the secondaries for the rail voltage stored in these rail caps, which actually have Alpine on them. I don't know if they manufacture them themselves or they just have managed to get a deal where the manufacturer will put their own heat shrink on the caps, but that's pretty cool. This third thing here is actually an inductor that sits in line with the power wire before it gets to the FETs, just prevents any noise making its way back down the 12 volt path to the vehicle and smooths out any noise that might be coming into the amplifier from the vehicle. The rectifiers after the transformers are these surface mount diodes, and these are actually thermally coupled to the heatsink as well from the PCB on the other side. There are some smaller rectifier diodes here after the transformer, which will generate plus minus 17 volts there or thereabouts, depending on the input voltage. And then those rectified voltages out of the secondaries get regulated by these voltage regs. We have plus minus 15 volts for the preamplifier circuit and that sort of thing. And we also have 12 volts ref negative rail for the output drive circuit, which we'll get to later. Over here is our remote turn on circuit from the remote wire. There's another voltage regulator up here, which seems to just be providing a solid stable 12 volts, possibly that then gets stepped down further to 5 volts or 3.3 volts for the MCU. This is a programmable IC that will be controlling things like protection circuit, soft start, and basically any other function the amplifier wants to have. And that stable 12 volt reg also probably supplies this header, which leads to the LED on the front of the case, just so the LED doesn't dim while the voltage fluctuates in the vehicle. And you can see a lot of this circuitry has this blue kind of coating on it. This is going to be some kind of epoxy or some kind of thing to prevent condensation or moisture from damaging any of these components if it sits on the board. Obviously in an automotive environment this is quite common. The PWM sent to the power supply drivers is supplied by our trusty old TL4 494. Great to see that still being used. Signal source obviously coming in on the RCAs, and then the preamp circuit is actually on separate headers, which is still in the case here. Got some op amps for applying low pass filter, high pass filter potentially, gain, etc. Then when the signal comes back into the main board, it gets converted into pulses ready for the Class D output section. There's lots of circuitry over here for each of the 4 channels, which will be converting the audio wave into pulses, doing all kinds of feedback stuff for lower THD. Probably lots of nice, clever stuff going on here by Alpine to make this Class D sound a little better than your average. Once the audio signal is in pulses, it's then fed to the output drive ICs. These are labeled abletech.com. You will struggle to find anything online about these. That's because they are an Alpine proprietary component by the looks of it, at least by some merit. They are basically an IRS 20956. Which is almost identical to the 20957, but with a couple of the pins flipped around, so they're not compatible. You can't drop in a replacement with a 20957, and I think they have tiny differences in functionality as well. But you can't buy these. The 20956 doesn't officially exist. There's no datasheet you can find anywhere for it. However, you can buy them from the likes of AliExpress or other Chinese vendors. And the output FETs are pretty cool. Underneath this thermal pad, we have these tiny little IRF 6775s. These are in a direct FET package, which is really cool. It can be called from both sides. The die size inside these will actually be the same as if it was in a 20220 package, but like I say, you can call them from both sides. Very tiny, easy to mount with automation. You can see the data sheet here, 150 volt parts, 47 milliohm RDS, continuous drain current of 28 amps, 89 watts of maximum power dissipation, which is a bit lower than I was expecting, to be honest, considering that this can be called from both sides. And with pretty quick pulses like we'll use in Class D, looks like they're fairly usable up to about 70 or 80 volts there, drain source. Above that, the current really drops off hard. With 12 volts worth of input, we have a rail-to-rail potential on the rail caps of about 66 volts, which kind of puts us in the perfect upper range of this FET before the current rating starts to drop off badly. We have a pretty fast switching frequency of 430 kilohertz. Pretty nice for full range Class D. I have seen faster, but that's just basically the bit rate or the sampling rate of the Class D circuit. And this is the amount of Class D switching noise you get through the inductor on the speaker terminals. That is pretty low, to be honest. Now, since this is Class D without any relays to isolate the speaker terminals when the switching activates, we would expect a little turn on pop when this comes to life. So with 12 volts going in, let's power it up and see if we can hear any pop from the tweeter or the woofer. Listen carefully. There is a tiny turn on click from the tweeter, but it is so unbelievably small. That is extremely impressive for a Class D amplifier, and you're never going to hear that in an automotive environment. Like, I had to put my ear right up to the speaker to even just about make it out. And what's similarly impressive is the lack of background hiss, which you do tend to get with Class D amplifiers on full range. You can see that the noise is still present there a little bit on the speaker terminal. However, the noise is such a high frequency that it is beyond the audible spectrum. There's nothing coming from this speaker whatsoever at the moment. It's currently turned on and turn off. No difference in background noise or hiss. Absolutely fantastic. Our idle current with 12 volts going in is between 1.6 and 1.7 amps. Bumping that up to 14.4 gives us 1.8. I forgot to mention, I love how the transformers are actually thermally coupled to the heatsink as well. You can just about see here in this clip that I made. The layout and the thermal management has been really well thought through. So that's pretty nice. But now let's take a look at the 5 channel. This is the X-A90V. So under the hood, we have practically the exact same amplifier that we just looked at. We have the same number of power supply FETs, the exact same model. We have 2 transformers, the inductor for filtering on the 12 volt side, the exact same rail capacitors. The front and rear channels are absolutely identical in every way. Same switching frequency, same output MOSFETs, and the exact same drive circuit. So it's basically the same amplifier for the front 4 channels. However, we now have a subwoofer channel, and we have 2 drivers, which are again the exact same driver. And the reason we have 2 drivers for the single sub channel is because the sub channel is in full bridge. So it's basically 2 channels for the sub, but in inverse polarity. We have pretty much the same switching frequency on the front 4 channels, 480-ish kilohertz. But for the subwoofer channels, we don't need quite as high of a sample rate. We have 284 kilohertz, which is still pretty high for a subwoofer channel, and it allows the use of more powerful but slower MOSFETs. As for the output FET model, it says on the package 0115AD. I have tried to search for all variants of this with direct FET after it, IRF, IR, with or without the AD. I cannot find find anything. I suspect it's a slightly lower voltage, higher current, slower, more powerful MOSFET used for the sub-channel here, but yeah, I can't confirm that. One thing I noticed, which is cool, which also applies to the other amplifier, is you see how we have thermistors, tiny little thermistors, right here by the FETs, not only by the sub-channel output FETs, also by the other output FETs for the front channels, and also right over here by the power supply FETs. In fact, there's one pretty much by each of the FETs. So if any area of this board starts getting too hot, then the amplifier will shut down and go into thermal, which is pretty cool. We also have larger inductors here. Now you may think that's because of the extra power throughput from the sub-channel, but really it's just to compensate for the lower switching frequency. The lower the switching frequency, the larger inductor you need to filter that frequency. And also with a lower frequency, you need a larger inductor for the same power throughput as you would otherwise have with a higher frequency. There's no additional rail capacitors for the sub-channel, so it's using the same rail voltage as the front and rear channels, but because the sub-channel is in full bridge, and also the fact that it uses slightly more powerful FETs, you can wire the sub-channel down to a lower impedance than each individual front and rear channel, and the fact that it's in full bridge means that there's quite a lot more power there. So where you'd only expect maybe 100 watts per channel on the front and rears, you can expect 500 watts from the sub-channel. And lastly, we have the mono, the X-A90M, supposed to do 900 watts into 2 ohms. So yeah, inside the mono, we have the exact same power supply setup again, high and low side, exactly the same power supply FETs as the other two amplifiers, same transformer setup, we have Alpine rail caps again, exactly the same auxiliary supply voltage circuit, and everything on the back here is exactly the same, TL5 and 4, all in the same positions. Same rectifiers, same voltage regulators, etc. So all looks pretty identical on this side of the board. The changes come only when we come to the output section. We have a pair of those same drive ICs, 20956S. So this is a full bridge mono amplifier. The output FETs right here are the exact same FETs that's used in the sub-channel of the 5-channel amplifier 0115, so I can't really seem to find any information on. Again, we've got 4 on this channel and 4 on this channel, 2 high and 2 low side. Slightly larger inductors than what it looked like on the 5-channel version, and lots of free space on the top side of this PCB here. And I'd expect the switching frequency to be the same as the sub-channel. Yep, it is 264, pretty much the same. These are definitely a nice series of amplifiers. However, one thing does worry me, that they're all surface mount, and that can be a bit fragile and delicate in an automotive environment, and surface mount parts are more prone to random component failure, which you'll see actually in an Alpine amplifier on one of my latest TikTok videos. Doesn't seem to be doing anything just yet. Oh, wait a minute. Do you see that? There we go. Look at that. What the f***? But the circuit design is really nice. It'll be very well optimized. Alpine engineers know exactly what they're doing. And provided you don't get hit with random component failure from the surface mount components, this should last you a very, very long time. Is it worth the price? That's down to you. You can definitely get an amplifier that sounds just as good for a fraction of the price of these. But if you plan on having it for a long time and you have the money to splash out, then absolutely a very good buy.